First, let's review today's agenda. First, I'm gonna introduce you basic Talos system, and especially I'm gonna focus on basic objects. I'm gonna introduce you on alignment from the top to the bottom, from the gun to the camera, and um, and then after presentation, I will show you how to do the basic dark field imaging, bright field imaging, and also at this afternoon we're gonna do high resolution time imaging. So and also we're gonna review how to align the Ceta camera, how to calibrate the Ceta camera for remove any artifacts in the Ceta camera. So by the end of today, I hope you will understand the basic Talos operation system and how know how to use the TA software, Relux image software, and understand how to set up the bright field time imaging. So also we're gonna you're gonna know how to do basic alignment for get good imaging, how to optimize the Ceta camera, like for the gang, gang correction, how to search, view, acquire imaging, and also we're gonna you will know how to optimize the image control resolution for by using different object aperture. Okay, first the little concept of the what is TEM, what is the STEM. So basically, for the time we have been go through your sample, and we have the Ceta camera. We have different camera to collect the different signal for generate different imaging. So basically, for the time imaging, we generate the diffraction contrast imaging, and so in that case, we can see if the image is gonna be coherent. We can see phase contrast imaging. We can see the in that way we can transfer diffraction to the atom imaging. We can also do high resolution imaging. For STAN, it's different story. Basically, the obvious different for the STAN, we have converged beam from very small probe, and then we scan the sample, and and then we have the annular detector to collect the transmit electron, mostly are incoherent, mostly or incoherent electron. In this way, we can generate this contract. We focus on generating Z contrast imaging to resolve the atom size, atom position. So yeah, this is the major difference, and you need to pay attention. And I also, of course, that's another thing we need to notice. For the EDS signal, it's we capture EDS signal above the sample. So because for the electron beam gonna interact with the sample during the X-ray, the X-ray gonna many refract about the sample. So we need some detector about the sample to collect this fingerprint elemental information. Okay, a little context, the difference between diffraction contracts and the soft contracts. So once the instant beam interact with sample, part of them gonna be absorbed by the sample. So for the bio sample, this amount of the reaction could be very significant. I mean, the absorbed electron by the specimen can be very significant. So that's usually, if you take a look at the bio sample, we mostly see the contracts from the absorbed electron. That means if you see dark contracts, means that region have the specimen and the electron inequality sample, that region more electron gonna be absorbed by the specimen. That's this is why we see darker contracts. Darker contrast means more absorbed electron. For the diffraction contrast, a different story. Especially the electron gonna go through the sample. We collect the electron transmitted from sample. So if you take a look at the diffraction pattern, basically we have central spore and outer ring for protocrystal. So the central spore gonna be the being transmitted from the sample without the interaction with the sample. So the outer ring spore is kind of electrical scattered electron by the sample, and if there is polycrystal, different ring indicate different orientation. So basically, contracts is indicated diffraction contracts. Darker region, maybe there is stronger diffraction contracts. That means crystal is very close to the zone axis, very close to its zone axis. Okay, that's a different. And in a TEM imaging, we have two image mode, diffraction mode and image mode. So basically, it's gonna tend to intermediate lens the strength of intermediate lens to switch between the two mode. In the diffraction mode, we see diffraction pattern. In the image mode, we see image contrast image. Diffraction contrast image. We have three different diffraction and the diffraction imaging in the in the materials. So we have amorphous, which is you see the diffraction pattern looks very blurry, but you're gonna see some ring. And also we have polycrystal. You will see clearly identify a small spot within the ring, and they different the ring size mean different orientation. And we also have single crystal. You will see periodic distribute the spot as indicate the single crystal structure, and the right side so your corresponding image diffraction contrast imaging. You will see for the polycrystal, you will see different contrast, different brightness, and some looks very darker. The dark green means that the green is at the zone axis. And for the single crystal, you will see very uniform contrast, and that means they have the same orientation. Different orientation have different contrasts in a diffraction contrast imaging. So for the diffraction contrast imaging, we generally use the objective aperture to increase the contrast. Okay, so for this also, I want to introduce you different between bright field and dark field. So for the bright field, basically we insert the objective aperture and select central direct beam. The direct beam means as I mentioned, there's no interaction between direct beam and the sample. So that means there's no orientation information within the central spot. So if we select the objective aperture, if you use the objective aperture, select the central direct beam, we're gonna see the perfect bright field with enhanced contrast by the objective aperture. The difference is if you use objective aperture, select the other spot, so we're gonna see the dark field imaging. So if we select the different orientation, use the aperture object. For example, here, if you select this specific ring, that means all the green with that specific orientation gonna be visible in dark field. So in the dark field imaging, if you see bright green, that's a green have the orientation we just select by the objective aperture. So if you want to see specific orientation, it's better to do dark field and use objective aperture to select specific orientation. So next, I'm gonna introduce a little bit different between these three systems. You guys have F200C, right? So this is for the F200C and we also have F200X and S. So There's no big difference between these three systems. F200 hex, we have for super X detector. Usually F200C usually come with dual X detector. So from either Oxford or Broker. So this is a major difference. Also, we have some difference between F200I and the 200XSC. So F200i, basically, we don't have touch screen on the surface on the panel. The main function of a touch screen is facilitate you to change the sample. It gives you step-by-step guide on sample changing. And also the big difference between L100C and the F200i, F200i 120C, it's Federman 10. It don't have the flag register. So my Talos F200i is come with a flag register, is a flag TEM. So that's a major difference. And the kV is different. The highest kV for the L120C is 120 kV. So next, I'm going to introduce you a little bit different the vacuum system and the safety. Basically, when you come in, you could check the Talos vacuum system. So here's the interface. You can see the different building block. In the center, you just see overview of the schematic of your vacuum. So IGP means ion gather pump, and the TMP means turbo pump. PVP means pre vacuum pump. So if you see something, if you see everything, see something green in the green status, that means they are running perfectly. If you see the dark, if you see the in dark red status, that means they're closed. But if you see attention to replay, if you see the fresh red color, that means something arrow pop up. So you can read that status. You see what kind of arrow you have. So basically, if you don't see the red arrow pop up, that means we're good. So here's different pumps for the pump down the vacuum. So basically, we have low vacuum pump, medium vacuum pump, high vacuum pump. So this three pump, they are the mechanism for them. They work differently. So basically, pre-vacuum pump is kind of a mechanical pump, and turbo pump and the turbo molecular pump and ion gather pump, they work at the very, especially for the ion gather pump, they work at a very high vacuum. So that means the PVP only work at the low vacuum, ion gather pump only work at a high vacuum. So basically, we have hierarchical pumping down schedule. First, we pump down the vacuum to from the long vacuum, from the air vacuum to the low vacuum by the PVP, and then we pump down the vacuum from low vacuum to medium vacuum by TMP, turbo molecular pump. Once it's reached to the certain value like 10 minus 6, then the ion gather pump can turn on to further pump down the vacuum. So if you cannot turn on the ion gather pump at very low vacuum because it's not gonna work. So here we're using different unit. So for easy reading. So and usually if you come here, you will see the unit for the vacuum is log. That means we use this log unit for easy reading. And here's the transformation between log and Pascal. Usually 28 log is equal to 10 to power minus 4 Pascal. So next, I think I'm gonna quickly go through this different objects and operation. And If you look at, so we have basically have four main object components in the column. The most important one is electromagnetic lens, and then we have electromagnetic deflector, and also we have stigmator and aperture. I'm gonna go through them one by one, right quick. So this is how the electromagnetic was look like. And we use this lens to generate a very strong magnetic field to condense the beam. So basically, we transfer the current to the magnetic field. So we have a lot of this kind of called winding. It's a lot of winding and a lot of current. A current gonna go through this winding, and gonna generate the magnetic field. So magnetic strength is proportional to the number of winding and the current. So the large magnetic field you have, the shorter focal point you're gonna have. So the focal point there is gonna be proportional to the voltage and the number of, in proportional to number of winding and the current strength. So with that said, this here is to give you a little bit more explanation. If you at the same voltage, but you have different current, then it means the large current you have, the shorter focal point you're gonna have, because they are in inverse the relationship, the in proportional relationship. So if you another story, if you have the same current but different voltage, then larger voltage you have, longer short focal point you're gonna have. So and the most next gonna introduce different between different aberration. Basically, in the microscopy, we have mostly four different kind of aberration: spherical aberration, cosmetic aberration, chromatic aberration, astigmatic aberration. For the spherical aberration, basically every lens is not that perfect; it's imperfect. So that means the beam goes through the different position of the lens gonna have different focal point. They're gonna focus the different point. This causes elongated beam. So how to eliminate spherical aberration? Usually we have spherical aberration corrector. So for Talos, we don't have that. We just use the aperture, C2 aperture, smaller C2 aperture to limit the spherical aberration. So we also, this is another side effect from the spherical aberration. If you source is not a center, then and also your lens is imperfect, then the beam goes through. Once beam goes through the lens, you're gonna focus a different point and generate a different size of the beam. Look like here. To limit this kind of effect, we're gonna also use aperture. The most common aberration is astigmatic aberration. Every day we do alignment, we need to correct this alignment. So that means this is caused by long uniform of the lens. If you have parallel beam around different direction, like X direction and Y direction, this parallel beam once goes through their aperture lens, they're gonna have different focal point. In this case, this is called elongation of the imaging. Here, this imaging, for example, it's elongated at around Y direction. So in this case, we need to correct this by stigmator. So for Talos, we have two-fold stigmator. It has two channel. Basically, it has north pole, two north pole, and two south pole. This four pole can apply different strengths of the magnetic field. So if you're being elongated at more around north pole direction, then north pole can apply stronger magnetic field to condense, to compress the beam, to correct the shift of beam. So this is how basically it is work to correct the beam direction. beam shape and the beam size. Next, I'm gonna go through with you the alignment step by step from gun to basically camera. So the first thing I would talk is gun. So basically we have two action, gun tilt, and the gun shift. So for the gun shift, basically your beam your source is away from the objects. In this case, we need to shift back to the objects. Remember that the beam still parallel to the objects, but just a little bit have a little bit the side movement, side distance between objects and the gun and the beam. In this case, we use gun shift to bring it back. Another scenario is your source is it's not parallel to the objects. It has certain angle between the optical axis. So in this case, we need to use gun tilt to tilt it back. We change the angle of the beam and optical axis. The most common case is we have both. We have both gun tilt and gun shift. So we have special alignment. We can use the gun. If it's usually we need to adjust gun tilt and gun shift to. You think about if you beam, it's not the source, it's not at the center. You will see your screen current is not maximum. So we usually use the gun shift and the gun tilt to find the maximum screen current. And well, after gun, we have condenser lens. One. This is the first condenser lens. This is so basically this will condense the beam. By changing the strength of the magnetic field within the C1 lens, we can change the spot size of the beam. So here we have 11 different spot size preset. Basically, number 11 means it has smallest spot size. Number 1 means it has big spot size. Biggest spot size. So in the hand panel, we can see here this the two buttons highlighted by the red here. If you push the left one, it's gonna reduce spot size. You push the right one, press the right one, it's gonna increase spot size. So learn that the smaller spot size gonna give you better resolution because it's gonna limit. It's gonna have less aberration. After C1 lens, we have C2 lens. So for C2 lens, basically it's gonna change your intensity. Intensity means the strength of the beam. So stronger magnetic field. If you basically we can go over focus and under focus by using the intensity knob in the hand panel. When we change intensity, basically we change the strength of C2 lens, and we're gonna spread the beam or condense the beam by using the intensity. So if you add a focus, basically in this case you're gonna get the minimum contrast. And you will see if you go over focus, under focus, this is over focus the beam. Usually your beam gonna focus above the sample. This is your focal point here. It's above the sample. And if you go under focus, you're gonna see your beam focus point is below the sample. Usually we go over focus because the beam gonna focus above the sample, you're got more current into your sample. If you go out of focus, because your beam haven't been focused there before reach a sample, so in that case you're gonna get a weak beam. So we also behind the C2 lens we have C2 aperture. C2 aperture is kind of a aperture to filter out the beam. It has different size. Large size aperture means more beam gonna go through the aperture, and means more light. So also large aperture means less incoherent beam means worse resolution. Usually, as I mentioned, we prefer to use smaller aperture to limit the spherical aberration. Behind the C2, we have condenser stigometer. So as I mentioned, if you see your beam elongated, you're gonna use the stigometer. It's true for the stigometer. You're gonna use stigometer to have a perfect round beam. So basically, in the hand panel, you can push the stigometer button here, and then use multifunction X and the multifunction Y button to correct the shape of the beam. It's a typical how uncorrected beam look like and the corrected beam look like in the TEM and STEM. So behind the C2 lens, we have beam deflector. So beam deflector can change your position of your beam. It shift the beam, basically gonna shift your beam back to the center. We have two ways to shift the beam. First, we can use the trackball here. It's gonna move the beam to the center. Also, we can use the multifunction X and the multifunction Y. So we got this two. This is deflector is kind of for double deflector. So it has double coil. So that's gonna introduce you a new concept, pure point. So that's mean if you the pure point it's it's basically if you have for both a beam, you're gonna have a beam shift and beam tilt. You're gonna do beam shift and a beam tilt. But if you do the beam shift, sometimes you're gonna introduce the beam tilt to your sample. If you don't beam tilt, it's gonna introduce the beam shift to your sample. So this is not ideal. Basically, we want to make sure when we do beam tilt, we're not gonna introduce the beam shift. So so this is why we need to adjust pivot point alignment. Pivot point basically is a point. It's like think about a swing. So if you have two persons, they have equal weight, and if you set up the right pivot point, the two person gonna swing. If you don't set up the right pivot point, this swing not gonna work. Same here. So if you set a perfect pivot point, in that point, we only if you apply the beam shift, we're not gonna apply beam tilt. If you apply beam tilt, we're not gonna apply beam shift, because this is very important. Think about it, if you, especially for high resolution imaging. If you have a beam tilt, that's good. If you do beam shift, and then if you pin per point, it's not aligned, you're gonna introduce the beam tilt as well. So in that's beam tilt gonna undo all the effort you spend in correcting the alignment, aligning the object length. So that's very important. So usually beam tilt is visible in diffraction and diffraction shift. Beam shift. So in that case, we set a beam shift. There's two pivot point alignment: beam shift, pivot point alignment; beam tilt, pivot point alignment. So since beam tilt is visible in diffraction and diffraction shift, so we usually align beam shift, pivot point in the diffraction mode. While beam tilt, pivot point are set in image mode because the beam shift used to be visible in image mode. So basically, here is a video show you the concept. So basically, we have a two preset position for the beam position A and the beam position B. Then use the multifunction X and Y. We change the pivot point at the around the objects. And then if you find the right pivot point, in that point, you're gonna see minimum wobbling of the beam. This is how we set our pure point. The important, you can see important of the pure point here. If you have bad pure point alignment, once you you tilt the beam, you shift the beam, you're gonna see your point, pure point on the sample gonna change. You basically here you tilt the beam, you don't want to see shift, right? But if you have bad pure point, you're gonna see the shift of your beam on the sample. So but the good when you have a good tilt point, you tilt the beam, you still have you don't introduce the beam shape. Your beam still seeing the same point. Your beam still look at the same point on the sample. Okay, after after C2 lens, we have after deflector, we have the object lens. Object lens is very important for focusing on a sample. If you go on your hand panel, you will see the focus knob here. You basically we change the focus, we change the object lens strength. In this case, we can do focusing. We have object lens usually have two object lens, upper object lens and lower object lens. And we load the sample between these two object lengths. So this basically is a gap between the upper object length and the lower object length. So the gap we usually is used for Talos F200C or S300X is about 5.4 millimeter, and for the usually for the bio sample, they require more contrast imaging. Usually they set up a very large pulpit gap to give him a little bit more contrast to imaging, and also they give more spacing for accommodating their qual holder. So usually for the qual EM, usually they have very big pulpit gap. So we need to set up their essential height. To put it, once you load the sample, we need to load the sample, or you need to set up the sample to the essential height. So this is we can move the sample, we can do alpha and beta tilting, tilt the sample around X, Y. Also, we can move this sample horizontally, and we can change the sample height. So the purpose for changing sample height, we need to put the sample to the essential height. This is very important. As I mentioned, if you put the sample to the essential height, when you do tilting, you're not going to see the side movement of your sample. But if you don't put your sample to the essential height, when you do tilting, we're going to see a lot of movement. Especially when you do tomography, this is very important step before you do tomography acquisition. You need to put the sample very close to the essential height. Next is lower object length. Again, we use the law is work with together with up object length to change to adjust focusing of your sample. Behind the object length, we have actually within the object length we have objective stigmator. So for other object stigmator, basically again we need to have the undistorted imaging. We use the object lens. We basically adjust the object stigmator based on the your FFT pattern. I will show you later. This is a very important step for high resolution imaging. The next alignment we need to adjust based on is correlated to the objective lens is rotation center. We want to make sure our beam goes through the objective lens, go through the center of object lens. So if you see when you go over focusing, under focusing on your sample, if you see the side movement, that means you have your sensing is not well aligned. So basically, you can select the latency element to minimize the movement, and then after correct, when you focus imaging, your central field of interest is no longer moving. Okay, and tomoframe is very necessary for HRTEM imaging. It basically is fine adjustment your latent center to make sure your beam goes through the objects. And after object lens, we have diffraction lens. So the lens is used in focusing imaging in low Mach mode, because as I mentioned, when you switch the low Mach mode, you basically shut off your objective lens. Then but in this way, you can use your diffraction lens to do focusing. And also, together with the projection lens, we can change the magnification. So we have different magnification mode. We have magnification mode. We have M mode, SA mode, MMH mode. For this four different magnification mode, we have different preset value for both diffraction lens and projection lens. So below the optic lens, we get intermediate lens. As the way I mentioned, if you change the strength of intermediate lens, we're gonna switch between diffraction mode and image mode. And also together with other lens, intermediate lens magnify the imaging. We have also calibrate the value for different magnification mode. We have a shutter coil behind the intermediate lens, below the intermediate lens. This coil for block the beam before it can enter to the projection chamber when no image is required. Shutter coil is faster than the beam breaker. The shutter is designed for protecting your camera. So, because when you take imaging, you basically you open the shutter, beam goes through the shutter and collecting by the camera, you get a imaging. But you see, you need a very fast shutter because you need especially if you want to do very low exposure, low you definitely faster shutter gonna give more accurate exposure time. By the way, beam breaker is designed for protecting a sample, right? If you don't want to, when you do the alignment, when you do the image analysis, you don't want to destroy you don't want to keep the beam on to destroy a sample. You can just use the beam breaker. But the beam breaker it's not good for protecting your camera because it's not fast enough. Usually we should just shutter. It's for design for the protecting the camera. After that, we have projection lens 1 and 2. This projection lens is together with other lens is for magnify the imaging. Different magnification have different preset value for projection lens. So here the little quiz basically as you know the position go over of the position of different lens. So basically we have C1 lens is on the top. We have C2 lens between the object lens and the C1 lens. And after that, we have mini condense lens. Usually mini condense lens is off when we switch from 10 to 10. Its half width creates more parallel beam for the diffraction imaging. And object lens here, and after object lens, we have diffraction lens, and then we have intermediate lens. We have P1 and P2 projection lens. And here the different diffractor. We have gown diffraction coil behind the gown. We have beam diffraction coil behind the C2 lens. We have image diffraction coil. It's basically behind the objective lens, and then we have the object segmented coil and diffraction segmented coil here, and the shutter coil is here. Keep that in mind. Beam diffracted coil is double diffracted coil. Gun diffracted coil is also double diffracted coil. You have two here. And the stigmator it's not a single coil. It's not a double coil. And then this is easy. We have a C2 aperture behind C2 lens. We have objective aperture within the objective lens. We have select area aperture and above the diffraction lens. Okay, any questions so far?
No.
Okay, I'm good. Then I'm gonna go a little bit more, introduce you camera, because camera is at the very bottom. It's behind the, it's below the projection lens, even below the fluorescent screen. So, so here's a basically use interface for the camera, for the CCD camera. Here the drop down, you can select different camera if you have. And then you can see you have the integration time, sampling, readout, the image size. You can do view, previews, and acquire. And you can have a setting. You can set up different preset for different purpose. If your sample is very big scientific, you can use low dose acquisition. If you want to go for high resolution imaging, or you want to acquire the diffraction pattern, you can use high dose mode. Here are the different setting for search and preview. This is a recommended setting, but it's not necessary. For the search, usually we use the full integration 9.1, sampling 2 or 4. For the preview, we use the 4.5. We do exposure 10.5, sampling 1. For the acquire, we use the 1.1. And frame size for the Ceta camera. So this sampling down. We have different sampling. We can choose different sampling. So there's two ways we can do sampling. We can do pixel, either do pixel binning or pixel skipping. For the 1x1 sampling, we can just do 1x1 binning, 1x1 pixel skipping. 1x1 means long pixel skipping. We can do 4K by 4A. We can do half readout. It's gonna be 2K by 2K. We have both high speed and high quality mode. For the 2x2, we can just do the binning, 2x2 binning. Again, no pixel skipping for 2x2 sampling. Full readout, it's 2K by 2K. Half loadout, it's 1K by 1K. We can do both mode. Here's the difference. So for 4x4 sampling, we have two modes. We can do 2x2 binning and 2x2 pixel skipping, or we can do 4x4 binning and no pixel skipping. In this way, you're gonna have very high quality readout mode. That means because you don't do pixel skipping, but if you do pixel skipping, you basically skip half of signal. Then in this way, you can do high speed readout. Same here for 8x8, you can do 4x4, 2x2 pixel skipping, or you can do 8x8 pixel binning. And you have two modes, high speed and high quality. And so as I mentioned, there's 3 dynamic range preset: low dose, medium dose, high dose. So for the frame, max count for one frame with sampling 1 is 8,000. So this is the max account, which is safe. If you go over this account, it be not safe for the camera. If you go with very long exposure, you might damage your camera because you're gonna get a lot of accounts you're gonna cause some artifact in your camera. So usually for the low dose, we just don't do frame sampling, and the max count is 8,000. For the medium dose, we can do 4 frames. This is a recommended setting. It's not necessary. You can do 6 or you can do 8. But for each frame, the max count you can go is 8,000. So that's give you 32,000 for 4 frames total. The high dose you can go 18. You can go 144,000. This is usually for high resolution imaging diffraction and imaging. This function is for like life science people. If you use very low dose for very low dose application, here you can select noise reduction to reduce the noise point in your image. So this will only work for Snapshot for readout full with sampling 1. When you set a very short, maybe small integration time. Rolling shutter. So during the continuous acquisition, if you select the camera to record video, you probably can go continuous acquisition. The rolling shutter, then you're able to select the rolling shutter. The rolling shutter can be selected which enable camera to read out the chip without shuttering. That means you don't gonna do shuttering. It just the rolling shutter gonna give you a higher frame rate for exposure time larger than this value, the 55 millisecond. For low exposure time, do not use the rolling shutter. Okay, finally, once you set up your camera, you can do imaging. For imaging, basically, you need to insert the camera and take image after at least 5 to 10 seconds for the best quality. So a lot of people just use the camera and then take an image. Usually, you should wait give the camera a little time until it becomes very stable. Usually, that time gonna be 5 to 10 seconds. Also, if you want to collect, if you want to do gain reference to remove the artifact in your Ceta camera, it's better to wait the camera cooling for at least hour until it's become very stable to acquire gain reference on the camera. Okay, here a little bit troubleshooting. So basically, if you see the camera is offline, you can just click to online to bring it back. And also you can refresh, if you lose the connection, you can refresh the connection. And also it's always good to check the Ceta current cooling to make sure you have cooling water on it's reached the stable, it's the temperature required for the Ceta camera. Okay. Before I go for hands-on time, any question?
No.
Okay. Then I'm gonna let me share my okay. So first, I'm gonna go through how to align the TEM and when you go in, what's the routine stuff for aligning the microscopy. So when it goes in, the first thing when you take a look is your vacuum. Basically, you can go here, you go vacuum overview. This is basically give you vacuum overview here. You see everything is okay. Low red arrow popped up, and also you can take a look at your vacuum supervisor, the sample window here. You see the value here. You don't see any red arrow pop-ups here. If you see some value highlighted in red, that means like this red. That means your microscopy vacuum for your microscopy is ready. So, and usually in this time, sometimes you see the cross column value, column value closed here. It's grayed out. You cannot push this button to open your column valve. And if you go far up here, you can go setting. You can change your unit Pascal. Usually for the lock this is a unit for easy remember. So for accelerator, it's always look at one. If you see this value go up one, that means you have some problem with your ion gap pump maybe. If you the column, this value is for imaging, it's better to below like 20. So if you go up like below above the 30, you may see this value turns into red. That means your vacuum in the column is not ready yet. Detection unit, this is a typical value. Buffer tank, this is also and backing liner, this is 50 around 50. This is a typical value. Also, you see here this is lighting level. If you see your lighting level below 20, you should add more liquid hydrogen here to make sure it's your column it's cold and it's cooled down to because this is adding liquid hydrogen definitely gonna it's cold trap piece. It's gonna definitely help you lower the vacuum further because it's a cold metal piece put into your column. It's gonna attract the molecule, and that's gonna help improve your vacuum. Also gonna help trap the absorb the organic vapor. That's gonna lower the contamination in your column. Okay, so you check the vacuum is good, and also this is if you go to the vacuum log vacuum test, you can see here this is a whole vacuum overview. You can don't switch to manual mode, always put that auto mode. So especially you know what to do, except you know what to do. So you see right now all states you don't see fresh red, you don't see any arrow. That means all good. If you hover over your mouse here, you will see the typical pressure for the gun, accelerator. You see everything is running. You see it here. This is the iron gap pump. You see it's running perfectly. You see the pressure there. This long running. And this is your turbo pump. You see speed 100%. It's running perfectly. So everything is good. You can see really different pressure for different pump here. I recommend when the machine is running perfectly, I recommend you take imaging of this interface to record all the value. So you know then you know the ideal value for different pump. Okay, once it's done, we know the sample is loaded, and then we can just open the corner valve, and we find the sample. We move stage, find the sample, which I have already did that. You to see your sample. So, and you find the first thing, you find the region of interest. Once you find the region of interest, you put your sample to your central height. This is two ways to do so. You go stage, you go put your wobble on. You see your sample is wobbling from -15 to +15. You can change this ranging, just use the slide bar here. You can do wobble sample from 10 to -10 or 5 to -5, any value you want. But at the beginning, usually we use the smaller value because more large value you use, more side movement you're gonna see. If you have so large side movement, you might see your sample go out of view. It's hard to adjust that based on. So that's the reason we should go small value first. But here, because right now sample is very close, so we just use the 15. So this will indicate right now you don't see too much side movement of your sample. This indicate your sample is very close to the center height. So you can push your center focus to bring defocus value to 0. And then you can go use Z high. Use Z high in the hand panel. Move the Z. If you see this is off, you see right now it's off. You see the side movement of your sample. If you go further, you see more. Right? If you see your sample move out of your view, then you probably stop the wobble. You choose a small value, you choose 5 degree, and you go wobble. You see, this is you give you a smaller movement. So in this case, you can use Z to bring it close. Once it's close, you stop worrying. You change this value to 15 again to do fine adjustment. Now you see sample when you also you can zoom in a little bit to give you more idea how the movement look like, and you say you can do a little bit of fine adjustment. Okay, this is close. You cannot remove the movement. You can minimize the movement, side movement. So, okay, this is pretty close, pretty good. Then you can stop wobbling. Then your sample is at your central height. Another way is to just look. If you don't prefer to use a wobble, basically you can just use you can take a look at the contrast in image. Basically, right now it's at the focus, right? You can just add using your height, right? You see your contrast is very minimal. You don't see the red edge, the Fresnel effect, Fresnel edge. So if you go here, let me show you. Right now, the stage is tempo is away from the center height. You see this red edge. This you see it's Fresnel edge. When sample is not at your center height, you will see, or not at the focus, you will see some this edge like this. So basically, you just you push the Z high, lower the Z high, or increase Z high to find a minimum contrast. Then you add your center high, and so now it's at your center high because you find a minimum contrast. You can double check with the wobbler. You see, it's very close. Okay, once you find your central height, the next thing we can do is to move sample to move to the vacuum region. The reason we're doing that because we need to condense the beam to take a look at your beam shape. If you condense the beam on the sample, you might burn your sample. So that's the reason we need to find the vacuum region. Also, we want to take a look at the beam size and the shape. We don't want the interference from your sample. So if you go on your sample, you have some interference. So separately, we go to the vacuum region. So before we go vacuum region, it's always good to like add a position to the stage so you can remember your stage position. So last time if you move out of you move to the vacuum region, and once that last time you want to go back, you just click this stage position here and say go. It's gonna go to the stage position. Okay. Once you go here, you can condense the beam. You say you can condense the beam and take a look at the beam. How beam look like, right? And then the next thing, you need to set up the parameter before alignment. So that means you need to choose this both sides, gun length, and also you need to choose the aperture. It's if you have a flag register, you can just go load the flag register. Say I want to load this, just that. That's gonna give you gonna recall all the presets you have. If you go fab out here, you can choose what kind of parameter you wanted to load. Say if you want to load your C1 aperture setting, you can check yes. And if you want to load your stickmeter setting or detector alignment setting, magnification setting, illumination setting, mode setting, flag register setting. So you can, if you don't want to load that, you can just uncheck that. If you typically want to load that, you can just, when you do that, you're gonna set. It's gonna set you back to the point where you store. So once you set our parameter, you can take a look. You can condense your beam, and then go to the magnification. Typically around several hundred thousand. I will go, and you can go select delete alignment. Use the beam shift. If your beam is off, use the beam shift to bring it back to the center. I will go for like 200, at least 200,000 this mag for the alignment. So you condense a beam at this mag, and you take a look at your beam. If you see your elongated beam, you can push stickmeter in the hand panel. Use the select condenser. Stickmeter, you can copy 1 to 2. Remember the initial value, and then use the multifunction X and Y to get a perfect round shape beam. Okay. You can push your center focus to normalize the beam. And once the beam normalized, you might need to use the beam shape to bring it back. Okay, so we did you put the symmetry to your center height. We go to the desert magnification, and then we adjust the shape of beam, and then we need to adjust the centering of C2. Typically, this couple way we can do C2 centering. We just put beam to use this first. We use beam shift to bring beam back to the center. Condense the beam. Use beam shift to bring the beam back to the center, and then we spread the beam like this, and then we then use if you see your left side movement, if you see your beam it's not perfect center, and then use C2 quick adjust C2, and then use multifunction S and Y, bring C2 to the center beam. And then you use intensity to check whether it's good or not. Typically very close. And then you can repeat this process. Use beam shift, bring beam back to the center, and then spread the beam. And then use this just C2 centering to the center. Okay. So this is the first way. Another way, you probably you can lower a little bit of magnification, and you can put a beam back to the center. And then you can use the C2 center C2. You when you click the C center C2, you see your beam is wobble. Use the multifunction SY to minimize the wobbling. Okay. Then sit down. Typically, when you have a good centering, C2 centering, when you go over focus, under focus, you will see your C2 have your beam wobble concentrically. Okay. Once you adjust C2 centering, and then next step you can do is you can adjust the gum tilt and gum shift. So for the gum tilt and the gum shift, usually gum tilt should be very close. And gum shift all same as the gum shift. For the gum tilt, usually we click the gum tilt and use the multifunction S and Y to find the max current. You take a look at screen current here. Right now it's 5.6. You say you find the max current, right? 5.4, 5.6. You say 4 point, that means they're not good. You need to move to location to find the max current. You say this is your edge of your lens, gun lens. You see, this is the edge, right? You don't see the current. You see the current goes down to 0.1. This is another edge. So you find this. Put it here in center, and then you find another edge here. This is another edge. So typically somewhere around here. It's your center. Okay. Okay, you find a gum tilt beam to the center. Next is gum shift. For the gum shift, typically first I go I go spot size like spot size 9. The reason I go spot size 9 is set up the low level magnification. Condenser beam, and then use beam shift to bring your beam back to the center. So the reason why we do beam shift at the spot sign 9, we need to set up the reference point, and then we go to spot size 3. We know we use the beam, we shift the beam to the back to the center, right? Use the beam shift. Now, but we still see our beam is not at the center, then we can use the gum shift. Then we know this is caused by the gum shift. We use the gum shift to shift the beam back to the center. We can condense the beam and then do very fine adjustment. And then we go back to spot size 9 again. We repeat the process several times to make sure we get a perfect aligned gum shift. So we should beam shift set up the reference center again. And then we go back, we sit down, and we go back to the spot size 3. We use gum shift. to bring it back to the center. We repeated the process until we see no big shift between the spot size 3 and the spot size 9. And then you see it's close, but we can use beam shift, bring it back to the center. And then we go back to spot size 3, use gun shift to bring it back to the center. You see now it's very close, so that means we're done. Okay, we're done. We set up the gun shift. So when set up the gun shift, we go to the design magnification again. We condense the beam. We go choose the spot size 5 because this is the spot size we used for the we used just now. We go back to spot size 5. You see you have a stick imaging. You can use the push stick imaging here, adjust stick imaging here. Okay. And then you can add a beam tilt. Just a beam tilt. Again, this is to make sure you got a pure shift or pure tilt. Because when you do tilt, you don't want to introduce shift. When you do tilt, shift, you don't want to introduce the shift. So okay. So beam tilt PPX and beam tilt Y can be affected by the U-central height. So if you change your sample U-central height, you should redo this element. And then we use the beam shift bring it back. So we adjust the gun tilt, beam shift, and beam tilt PPX, beam tilt PPY, and then we also did the C2 sampling. The next thing we needed to do rotation center. To do rotation center, we need to find a sample. We need to do rotation center on a sample. So we select this point, we just store, and then say go to. We find a sample, and then we condense the beam. We spread the beam to see the sample. We lower the magnification a little bit to see the sample. Once we see the sample, we can just click rotation centering. You see the wobbling of your sample feature. So you use multifunction SY to minimize the side movement. And you can zoom in to do fine adjustment. Okay, now you see it's pretty good. Okay, we're done with the rotation center. Then we can take an image. So to take an imaging, we need the insert camera to get an imaging, right? So so first I'm gonna tell you how to take a bright field imaging. Next I'm gonna tell you how to take a dark field imaging. So to take a broader field imaging, there's two choices. First, you can use if you say your contrast from your sample is good enough, then you don't need to use objective aperture. But if you say your contrast of from your sample is very weak, you need to use objective aperture to increase the contrast. So first, I can take image without objective aperture. So you go choose software we can use for taking the imaging. One is TA. So for the TA, we can just use the camera here. And you can go flap out here. This is setting, low dose, medium dose, high dose. We can just use the medium dose. We can set a medium dose. Then it pop-ups give you a choice. This is like frame combining. So first we're gonna do search first. So for the search, we probably don't want to do the frame combining. So usually we do frame combining 1. For integration time, as I mentioned, 0.1. For binning, we do 2. We do 0.1. 0.1 probably choose to weak 0.2. And then we can do quick search. You can set a readout area full or half. I want to say full region, so I go full. This is your search, and again, quick search. In the proper window, you see here. Let me see. It's here. Okay, it's in another window. So you will see in different window. I need to bring that up. Okay. Okay. Now you can see the window, right? This is your search, and then you can leave the screen, and then you get a search view. Let me make it small. Okay. This is your search view. You can find a good region. Do a find now is your chance to do focusing. You can do focusing. Use the focus lock here in the hand panel. Once you find a good focusing, then you can set up the parameter for acquiring. You can go here. You switch to the acquire and stop the view. And then you stop the view and then set up acquisition parameter here, and go. You can go printing 1. Set the exposure time 0.5. You don't want to do binning. That means you can acquire 4K by 4K imaging. You do integration 9.5. Whether you want to do frame combine, probably you can do no frame combine at first. Then you can acquire image here, and you see acquire. I need more space. Interesting. Okay. Let me take a look at my disk. Just to get more space. Okay. That's good. And then you get a imaging, right? This is the imaging you just got. So as I mentioned, this is how we basically take an imaging. So because you don't want to, because you might be confused. How do we set up the integration time, right? Because I just set up like 0.1 for the search, and this is the 0.5 for the acquire. You say you get enough contracts, which is good. You don't always approach your camera. You don't have extra bright spot. That means it's good. And also, as I mentioned, the max count per frame is 8,000. So in this case, you can go side panel. You can go here. You take a look at data information object. You select display. Maybe object information. You can put spot in. Yeah, you put spot. You go here, put a star, and you can go here. This is your spot, right? You can search your spot. You can put a spot in the brightest spot, like here. You can take a look at your intensity here. And also you can read the dose. So basically I want to pay attention to intensity. Right now it's 3,359. This is 3,000 almost. So as I mentioned, for the one frame, we can, the max count is 8,000. Right now it's about 3,000, so it's about 4,000. It's so so you make sure you get the, you make sure you go over, you find a brightest spot. So that means the max count within the image probably around 4,000. Then you can do a sample calculation. So because right now integration time is 0.5 seconds. So that means if you go 1 exposure time here, 1 second exposure time here, the max count it may go up to close to the 8,000, right? Because we don't want to go over 8,000. That means the max integration time we can set is 1 second. In this way, we can get the more contracts, and why keep the the max count below 8,000? Because we want the count below intensity below 8,000 to keep the camera safe, right? You can go profile here. You can draw line profile. This is your line profile here. You can go over to make sure you don't have. You can go to make sure you don't have counts. You can read the count there. You see the average count, the max count is about 3,200, right? And you can use keyboard here. Okay. So this is your line profile. Okay, there you see it seems that our count is 3,200. So and then we can, it seems we have, if you feel this contrast is good enough, then you can stop. But if you want more contracts, then probably you can go acquire, increase the exposure time to 1. As I mentioned, you cannot go beyond 1 because after beyond 1, because you know this you get almost 4,000. That means around 1 exposure second for 1 frame, you might get something come close to the 8,000. So if you go beyond 1, that means you might overexpose to your camera. So let's go to 1. Then in this case, you can get a more spacing. You can get more contrast. Okay, this is the exposure at the 1, and then you can draw a line profile. And say your contract right now is over 6,000, but it's not. It's well below the 8,000. So you can do a math to calculate the the max integration time can go based on the max count. Okay. Then you might ask, what if I want to further increase my contacts? Because you cannot increase your integration time anymore, right? But what if I want to further increase the contacts? There's two ways. First way, you can do frame integration. Because right now you only have one frame, right? So you can combine multiple frames. That means you can go for, let's say I want to combine 2 frames. And each frame is 1 second. That means integration time gonna take you 2 seconds. So then you're gonna have 2 frames. Each frame is 1 second, right? Then if you combine 2 frames, the mass count the mass intensity allowed is 16,000, right? It's because you have 2 frames. It's not 8,000 anymore. So you have 2 frames. The max count allowed is 16,000. If you have 4 frames, the max count allowed is 32,000. So right now we combine 2 frames, and with integration changes to 2, we can acquire another imaging. Okay, and then you say this is your imaging. You can do 9 profile. You say right now your intensity, you count, you get a lot more counts, right? You get a 12,000 counts, which is safe because you don't want to go over 16,000. 12,000 is good because you have 2 frames. You combine 2 frames. This is a way to further increase your contrast, increase your intensity, right? Increase your signal to noise ratio. Okay, this method is extremely useful for diffraction pattern imaging. I will tell you the reason tomorrow when we do the diffraction imaging. Okay, this is one way to increase the contrast. Another way, you can just use the one exposure time, 1 frame, but you want to increase the contrast. You're not going to increase the count. So by combining more frames, you're going to increase the count. But if you use objective lens aperture, you're not going to increase the intensity count, but you're going to increase the contrast. That means your darker region look more dark, your bright region look more bright. So let's do that. First, you go to select object aperture. You can go 100 first. To do that, I need the put screen down. Now I insert the objective aperture. How do I know the position of my objective aperture? As I mentioned, if you want to do bright field, perfect bright field, you want to make sure your objective aperture select the center of your direct beam. But how do I do that? We need to go to the diffraction mode. We push diffraction mode. In this way, we can see our diffraction. And then you can see your objective aperture. You can change different mode. And then your you see this is your diffraction pattern. And you see the position of your aperture, right? You need to use aperture, adjust the position aperture to move the aperture to the center. And they say down. Then you can go out of detection, and you get your imaging. So and then you can leave the screen, and then you go search again. So this is your search image. You see you have more contrast, right? Compared to the image you would get before. This is the search view. Because you see this region look more, you have more contrast. And then you can take a look how much counts you have. You see you have similar counts, you still get 3,000 counts. So the object capture gonna increase your contrast, but not gonna increase your count. To increase count, you need more exposure time. And then you see you can take imaging. You can just acquire. You know, it's right now the 0.2 second. Oh, sorry, my bad. Because just now I changed the intensity, right? So the counts will change a little bit. So now you need to calculate your exposure time set for the exposure. Right now the max count is about 3,000 for one frame. So to acquire imaging, if you go acquire, it's 1 second that you all exposure imaging. So so 0.2 seconds, then you need only the max time you can go is 0.4, right? Because 0.2 you already get it 3,000. So you do a sample mass. Right now we go 0.4, and then acquire. This is annoying. Okay, and then we get night profile. You see, oh, because we did the binning, right? Okay, this is so 0.4. Right now we got 16. So let's mean we can go 0.5. We can go, if we go 1 second, acquire. One second is about 4,000. So that means in this case we can go almost 2 seconds. But 2 seconds you're gonna some region gonna overexposure because you're gonna add up to 8,000 more. For the search, you see the count is different, right? For the search, you found different. Your integration time for 2 seconds, but you get a count over 3,000. That's because you use the binning. So you can, if you choose binning, you bin up you basically add more signal. So that means if you go binning 1, you go binning 1, low binning, and you should change this to 0.2 again. So you see binning 1, you count 0.2 seconds, you only get 800 counts. Max count is about 800. If you do binning 2, still 0.2 seconds, change back to 0.2 seconds. Your count increased 4 times, right? Your count increased 4 times. So this is another way to increase your count in your imaging. But so if you you want to increase your count in your imaging, two way. First, increase the integration time. Another way, do the binning. And if you want to increase the contrast, there's a couple ways. First, you can increase the integration time. Also, you can use the objective aperture, increase the contrast. And also, you can do binning. So here's the thing. So if you do binning, you lose your image size. So you do binning 2, you only get 2K by 4K, 2K imaging. If you do binning 4, you're gonna get 1K by 1K imaging. Because if you do the binning 1, binning 2, that means your mass count you can get is 32,000. Because so if you do no binning, your max count is 8,000, right? If you do binning 2, your max count is gonna multiply 4. It's gonna be 32,000. So that means even you go 0.5 seconds, then you get the count over 8,000. Then you are still safe. You're still safe. The camera is still safe because you're not because you're basically your count increase by changing the binning, right? Your camera is still safe because the max count allowed is 32,000. You can even go 1 second here. Now your camera is still safe. It's 16,000. Don't go over 32,000 because the max binning, the max count is 32,000. Now, so this is some people maybe sometimes feel confused because when you use binning, you basically your max count for the camera change based on the binning number. Okay. So if you're binning 2, your max count is 8,000 multiplied 4. If you're binning 4, your max count is gonna be 8,000 multiplied 16. Okay, this is a couple way. How do we use some camera safely? How do we make sure we improve the contrast while keep the self camera in a safe exposure range. So couple way, as I mentioned. First, you take an imaging, you go from use a very low exposure time, like I go on 0.1, and then I use a binning 1, maybe 0.1, binning 1, and then take a look. My count, I say I get a very low count of 400. I do binning 1, I have no frame combining. That means in this case, the max count is 8,000. Right now, I only get 400 counts. That means I can increase my exposure time almost 20 times. If I go 1 second exposure time here, the max count I get is about 4,000. So if I get 2 seconds, max count is gonna be over for 8,000, right? I definitely don't want to go 2-second exposure time. But what if I want to further increase my count in my image? To Merced, you can do binning. If you do binning 2, and you keep use the same second, you can use 1 second. Binning 2, In this case, you can get 16,000 counts. It's over 8,000, but still safe because you're spinning, right? So now the max count takes you 32,000. Another way, you can still use the binning one, but use more frame combining. You can use binning one, but use more frame combining. So frame one, binning one, you get 4,000, and you can go for stop the view and go for 4 frame and 4 seconds. In this way, you can get 16,000 counts as well. In this way, the max counts tend to be 32,000 as well. You see, you get 16,000 counts. But let's say, because you have 4 frames, you divide 4. Right now, the count for each frame is about 4,000, so it's below 8,000. So it's good. Okay. And next, I'm gonna use the you can choose different size of the aperture to increase the contrast. The contrast concept is different from count. So the count means you have more pixel, you have more counts within the image for each pixel. But contrast means your contrast image look different. Your bright region gonna look more bright. Your dark region gonna look more dark. That's a contrast. So you can use objective aperture to do so. First, we do 1 frame. We change this time to 0.5, 0.5. We do 1 frame, and then okay, we stop the view. We load the screen. Now we get 100 aperture, right? I want to use smaller one. I go for 51. 51 give you more contrast. We go to diffraction mode. We make sure to see the position of the objective aperture. You see this is the aperture position. We go here. We can focus a little bit. And we adjust the position of objective to make sure it's centering. Okay, centered. And then we deselect the objective aperture, and then deselect adjustment, and then go diffraction. Go out of direction. And then you see you get more contrast. You can take a look at imaging. We leave the screen. We go search. We select search view. You see? Now this region looks more darker because you use the smaller aperture. So smaller aperture means more contrast. Right? Small aperture means more contrast. We can acquire them. That means the compression. We just keep it go for acquire. So we just use 4K by 4K, 1 frame. We acquire imaging. So this is use 150 aperture. So I think, yeah, this one is no aperture. This one is, I think it's 50 or 100. This one 100. This one no aperture. This one is 50. Even though you can say when you use the smaller object aperture, you're gonna get more contrast. We can go more. We can go even select smaller one. We can select a 21. We need to go to diffraction mode to adjust position of aperture. Don't go natural. So you see your aperture is very small. So you need to find your center spot. So let's say this is center spot, and then we go to diffraction. So and then you leave the screen, and you acquire an imaging. Use sense setting. You see, it's your contrast further improved. This is your 50 aperture. This is 20 aperture. Your contrast is further improved. Sometimes it depends. It depends. So this is 100. Oh, this is 20, 50, 100. You see the difference, right? So if you have a very small particle here, it seems this one looks better. Okay, this is how we use different apps for that. Okay, any question?
So I'm a bit confused about the binning. So when you change it from 1 to 2, the count rate is it doubles?
It's the count rate is 4 times.
Okay, and then if I change it to 4, it'd be like
16.
Okay, so it's like a factor 2 squared, or whatever, 2 to whatever the binning number is.
Yeah, so basically if you do binning 2, it's gonna binning your basically your it's 2 by 2 region. You're binning your 2 by 2 region to be 1 pixel. 2 by 2 region, basically you have 2 pixel, right? You make 4 pixel to be 1 pixel. That means your count here gonna you count in that bin the pixel gonna increase 4 times because you have
Okay.
you have
I get it.
Yeah, and
Okay,
if you
that makes sense.
Yeah, same thing. If you do 4 binning 4, so you basically you have 4 by 4 region, right? You're binning this 4 by 4 region to be 1 super pixel.
Okay.
Okay. Cool.
Okay, I get it. Thank you.
You're welcome. Okay, let's do a break. I need to add a little bit more liquid here. Let's take a break, and then after back, we're gonna do the dark field imaging. Is it okay?
And then, did you go over the coma-free alignment, or that's later?
Yeah, we're gonna go there when we do high resolution imaging this afternoon.
Okay.
Yeah, because right now we just focus on low mag imaging and the dark field.
Okay.
Cool. Okay, that's now is 48. I will be back in probably 15 minutes. I need to add more equation.
Okay.
Yeah, talk to you a little bit.